Good afternoon, people. Week 8B is this particular presentation. So we're at the end of week 8. In 2 weeks, we're going to have a midterm. Just a second. And so, accordingly, this is the cutoff for the second midterm. Next week's coverage material won't be on midterm 2. I'll review it next week. Probably on Monday, I'll post something to get you prepared for the March 9th, 3:30 p.m. ASB AQ 3181. That's where we're having the exam. So some of you did very well. I want more people to do very well. I'd like to, like I said before, get you in the sort of middle of the distribution, around the 50% point. I'd like you to obviously move your grades higher. The test isn't going to be any more difficult than this one. Same kind of idea. If you've paid attention to what I've told you, I'm not going to throw any curveballs. And just it'll fare well for those that work harder. Okay, let's just finish this week off. We're going to talk about distributions now. This ends chapter 6. This is 6.5. Okay, this is very brief. I should have just done it with 6A, but I wasn't feeling like I wanted to go on anymore. So here this is what we did before. We reviewed both permutations and combinations with repeating characters, and derived a formula for combinations with repeating characters. Remember, we converted everything to a binary system of stars and bars, and then we now could reduce the problem to something we've done before, which is combinations with repetition. We related this formula to integer solutions of equations as well. And today we want to discuss the theory of this. All fits in with distributions, and you'll see why. That is distributing objects. You can distribute identical objects into identical containers, distinct objects into identical containers, identical objects into distinct containers, and whatever the word I start, I don't know. Anyway, it's just a permutation of those two things. Okay, of distinct and indistinct. So here we go. This is the way it works. We have distinct objects being put into distinct containers. We want a formula for that. Distinct objects being distributed into identical containers. There's a formula we want for that. Identical objects into distinct containers, identical objects into identical containers. Now, it turns out we can't do all these. Some of these, at least one, is too advanced for this course, and it's actually for a much more advanced discrete math course than this one. So, it says also with constraints. Okay, with constraints, that's what it says at the very bottom there. So this is what we have derived so far. You can see, obviously, these are permutations and combinations without repetition. This is permutations with repetition. We saw that right at the very beginning of this chapter. And this is the one we derived for our combinations with repetition, okay, which we basically reduced our combination problem into a binary set, which you can therefore solve using combinations without repetition. Okay, so that's how we derive that formula. So how do you permute indistinguishable objects? Well, how many different strings can be made by reordering the letters of the word SUCCESS? So, these examples are simple. I'm not going to write them out for you. It's easier if we since there's so few of them, we just walk through them. So there are several possible positions for the 3 S's. 1S, 2S, 3S, the 2 C's, and 1 U and 1 E. Okay, that's what we have here. So the 3 S's can be placed in 7 choose 3 ways. 1, 2, 3, 4, 5, 6, 7. There's 7 of these, and there are three of these objects, right? So we've got 7 things. That's N, and R is 3. It's 7 choose 3. That's obvious here because there are 3 C's. S's. The two C's can be placed in 4 choose 2 ways because now we've reduced this 7654 down to 4 remaining, and then reduced to 2 choose 1 with the U and 1 choose 1 with the E. So we've gone from 7 to 4 to 2 to 1. You can see how we are basically coming up with this formula right here, which looks amazingly familiar. It almost looks like the multinomial formula, and that's what it is. So we've already introduced this before. There's no need to prove it. We've done it before. We did this in, I don't know which presentation it was. I can't remember now. But we called that the multinomial theorem, right? Yes, going back to the first presentation in this chapter. So we had the rule of thumb, just to review. Then we had the rule of product, the rule of subtraction, I should say, which is inclusion exclusion, but you can also call it the rule of subtraction, just to put it all under one nice umbrella of addition, subtraction, that's inclusion exclusion, and the rule of product, and then the rule of division, which we aren't going to apply in this course, rule of division. Very simple, very straightforward. But then soon afterwards, we came up with the multinomial coefficient formula. And that is exactly what we're applying right here, okay? So that's where we are. It's just a repeat performance. There's no need to prove it because it's already been done. So let's look at the integer solutions to linear equations again. So the following related type of problem is how many non-negative integer solutions are there to the equation a plus b plus c plus d equals 100. Now, we've already seen this in the previous presentation. So in this case, we would have 100 A's, 99 A's, and 1 B, or 98 A's and 2 D's, okay, etc. So we see that the number of slots R is 100, right? That's what we've already seen before. And we are arranging over 4 categories, okay? So these are the 4 categories, A, B, C, and D. And so the number of partitions then is just from this formula that we've had already. There are 103 choose 100, 103 factorial over 100 factorial, 3 factorial, non-negative solutions to this. This is just applying the formula for combinations with repetition, as we did in the last chapter. Okay, so here's what we're realizing. We're realizing that the number of integer solutions of the equation x1 all the way to xn of this sum equal to r. Okay, so there's your n, there's your r. N slots, n categories, and r objects altogether is the same as the number of selections with repetition of size r, of a collection size n. So that's what we learned, with repetition, with combinations with repetition. So here we have again determine all the integer solutions to this. Well, here now we have applied some constraints to the same problem. And so we have this same problem again we did last time, except now we have an added constraint. So as Grimaldi does it, this is actually a Grimaldi problem. Allowing variables to equal 0, those are stars, and bars applies, okay? Allowing variables to be 0 implies stars and bars apply, okay? So represent 3 bars. 3 bars. Boy, what's this? Anyway, 7 stars. Okay, 1, 2, 3, 4, 5, 6, 7. So 3 bars and 3 bars and 7 stars. That T just doesn't belong there. What the heck is this? Divide into 4 parts? I've got to fix this slide. Total number of symbols is 7 plus 3 equals 10. Yes, we know that. So choosing the position for 3 bars is 10 choose 3, and computed it's 120. So we interpret the equation as distributing 7 identical objects among 4 distinct containers. There it is, just like we've done already. I'll fix this up after. So this then is the ultimate solution or conclusion that we have here. Not only is it the solution to integer equations, and as well as combinations repetition. It's also the number of ways R identical objects can be distributed among n distinct containers. R identical objects, you have to make sure you get this part right. It's not distinct. It's not distributed. It's identical objects to be distributed among distinct containers. Okay, so you can read this. This is just a little added business. Well, I read it for you. In terms of distributions, part C here is valid only when the R objects being distributed are identical and the N containers are distinct. Okay, so like the containers can be labeled A, B, C, D, they're distinct. Okay, whereas all of these objects being distributed are identical. So, how many ways are there to place 10 indistinguishable balls into 8 distinguishable bins? Indistinguishable balls into 8 distinguishable bins. Well, that's this right here. Identical objects into distinct and distinct bins, okay? So that's exactly what this problem is. And we can see that it's just simply applying this formula. The number of ways to place 10 indistinguishable balls into 8 bins equals the number of 10 combinations from a set with 8 elements with repetition allowed. So that's an easy application of this problem. 10 minus 8 plus 8 minus 1. Choose 10. Okay, so that's just the formula we learned in combinations with repetition. There it is right there. Distributing objects in containers. Let's just move forward with this. Distributing objects into boxes. How many counting problems can be solved by counting the ways objects can be placed in boxes. So same thing. I'm just sort of repeating ourselves here. The objects may be either different from each other or identical. The boxes may be labeled distinguishable or indistinguishable. This slide is almost redundant. I'll probably remove it too. So we just saw that the problem of combining with repetition, the problem of combinations with repetition is identical to that of distributing identical objects into distinct containers. So here, the number of the containers are distinct. They are numbered, for example, whereas the balls are all identical. All right. So once again, repeating what we've just derived. We have already developed a method of distributing distinct objects into distinct containers at the beginning of this presentation. Permutations with indistinguishable objects. Permutations with indistinguishable objects. So distinct objects into distinct containers is permutations with indistinguishable objects. How many ways are there to distribute hands of 5 cards to each of 4 players from the standard deck of 52. I hope most people out there know how to play poker, know what a deck of cards is. There's 4 suits, clubs, diamonds, hearts, spades, and each suit has 13 cards. That's ace can be either 1 or 11. Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King. Actually, ace goes either 1 or to the top of 13, not 11. So this is easy, an easy combinations problem. Actually, you can see that we use the multinomial theorem to do this, or we could just, well, this is the multinomial theorem. We could have applied it just directly, right? So 5 cards, 5 cards to each of 4 players. Well, first you choose 5 out of 52. Then you have 5 less for the next player. That's 47. Choose 5, and now you've taken another 5 out, so it's 52, 47, 42 now, and then 37 for the 5th player. And so you just work all this out. It ends up being the multinomial formula. So the solution to example 8 equals the number of permutations of 52 objects with 5 indistinguishable objects, okay, of each of the 4 types, and 32 objects of the 5th type. This equality can be seen by defining a 1-to-1 correspondence between permutations of this type and distributions of cards to the players. Once again, this equality can be seen as defining a one-to-one correspondence between permutations of this type and distributions of cards to players. So they're identical problems, just different kinds, different ways of describing the same mathematical structure. To define this correspondence, first order the cards from 1 to 52, then cards dealt to the first player correspond to the cards in the positions assigned to objects of the first type, permutations. Similarly, cards dealt to the second, third, and fourth, just like we went through, correspond to cards in the positions assigned to objects of second, third, and fourth type, respectively. The cards not dealt to any player correspond to cards in the positions assigned to objects of the fifth type. Okay, this is a one-to-one correspondence. One-to-one correspondence is like the set of positive integers as a one-to-one correspondence to the set of integers, one-to-one. Although one's a subset of the other. So that's this formula. The multinomial formula is distributing distinct objects into distinct containers. We just saw that here. So remember that. Now we've covered two of these guys right here. There, we've covered two of these already. Okay, so we're moving on now. We got one more to do, and then the fourth one is beyond the scope of this course. All right. So that's what this is. Okay, the multinomial formula applies. Advanced distribution theory. Okay, those two are the easy ones. I'll summarize what they are shortly. But now we get into sort of troubled territory here. Things get very complicated. Here, distributing distinct objects into identical non-empty containers. No container can be left empty. Can be left empty. All of them have to be occupied somehow, and that requires this function. We'll derive this when we get to chapter 9. Where it'll be most important in terms of counting onto functions. Onto functions, we'll define what that is. There's onto one-to-one. So those two different types we'll talk about. It has to do with codomain and domain, how they map. Remember that a function maps exactly once out of each element of the domain to the codomain. And we'll cover that when we get there. So this is a Stirling number of the second kind. Just accept it for now. This is what we're going to be dealing with. That is the way we'll find out to distribute distinct objects into identical non-empty. Now, non-empty is the proviso containers. But I'm just going to leave that for now as just, you can look at it. I'm not going to prove anything because we get into the detail of the utility of this when we derive the cardinality of onto functions. Okay, so Stirling functions of the second kind, that's what they look like. N choose J Stirling. Okay, I don't know how you'd actually say that. The Stirling function of N choose J, I suppose you would say it. It's this sort of intimidating looking formula, but it's really not that bad when we get into it. So it turns out that the number of ways to distribute N distinguishable objects into K indistinguishable boxes is given by the summation of these various Stirling functions, okay? So that's the formula for it. We'll find out later how to derive it. So let's just say that this is an open form expression. I think I've described this before. Closed form versus open forms. Most functions in mathematics are open form. They're functions that look like this. They're some kind of series, okay? So this is open. You've seen this in a geometric series, and that's its closed form representation. We don't have this luxury in general. Most functions are not representable in closed form. Okay. Well-known functions, that's what we mean by closed form. It's, not an open form expression like a summation or a recurrence set, okay? So here's a well-known function, okay? The quadratic equation. I guess I just use that as an example, meaning elementary functions. Constants, one variable x, elementary operations of arithmetic, nth roots, exponent, and logarithms. Those are well-known, well-understood functions. So here we have basic arithmetic, um, and not much more to it. So that's a closed form expression. Open form means it's not expressible in closed form. Here are some examples. You'll learn about these later in mathematics and physics, especially in physics. Bessel functions, they look like this. Legendre polynomials, associated Legendre polynomials of the second kind were one of the most important functions of my PhD thesis. Chebyshev polynomials, those two linked together, were used in tandem to produce solutions to advanced partial differential equations in my life as an applied mathematician. We will return to Stirling's in chapter, that's supposed to be chapter 9. This is Grimaldi, chapter 5. Unfortunately, I didn't change that. So the identical objects into identical containers is due to the theory of partitions. This is sort of an artistic way of describing that. It's just a visual for you, and it's beyond this course. That's all that's to it. So here is your summary. Distinguishable objects into distinguishable objects to distinguishable boxes is the multinomial formula, and distinguishable objects into distinguishable boxes is the standard formula for combinations of repetition. And what do we have here? Distinguishable objects into indistinguishable boxes. See, this is indistinguishable now. Is with Stirling functions, and indistinguishable and indistinguishable is this crazy thing called the theory of distributions, which we won't do. There are 9 ways to pack 6 copies of the same book into 4 identical boxes. The number of ways of distributing indistinguishable objects into k indistinguishable boxes. Okay, so that is indistinguishable and indistinguishable, and we won't cover that. We can't do it. So we leave that one blank right here. That's what we just talked about. Identical into identical. That's what this was. Identical into identical. And so we don't have a solution for that, but we do have a solution for Stirling functions, was a distinguishable into indistinguishable, distinguishable into indistinguishable. That's this one here. And then we started off with permutations with repetition for distinct into distinct. So that pretty much covers it. I know it's hard giving these lectures when there's nobody out in front of me. I'm kind of talking to myself. And so that's why I tend to, I guess you might say I run on pretty quickly because there's no resistance. There's nobody out there asking questions. It's difficult. It's new to me, but we'll see how it works out. Okay, so here we can also view this all with constraints. This is just those of you that are interested. You can look at this. You don't have to. If you find it too intimidating to look at, you're not responsible for it. So. But that is, I like to summarize things as completely as possible because sometimes we have, some people that find this stuff interesting, although it's beyond the scope of the course. Right. Yeah, well, I'm just repeating myself here. Okay, never mind all that. So now, people, you've got chapter 6, and that's the cutoff for the midterm. So don't, we've got 2 weeks before we have to have it. It's it's 2 Mondays from now, so it's less than 2 weeks, week and a half. You've got that long to study for it, and I know that you'll do very well this time. To expect, the kinds of questions I ask. So I really want a higher distribution. We'll review it on next week on Monday. And until then, I bid you adieu. Bye-bye.